Okay, we're now going to look at a linear, second order, constant coefficient, inhomogeneous ODE. Now remember that the part that makes it inhomogeneous is the fact that we no longer have 0 on the right hand side. We've got this e to the 3t. We're going to use the method of undetermined coefficients to solve this problem. That's where we make a guess for a particular part of the solution so that the right-hand side matches. We'll note that, this is the table from the notes, we've got a right-hand side that looks like e to the mt, where m is 3. So this yp will be our guess in this case. But the first step is to solve the associated homogeneous problem. That is YH double prime plus 4YH equals 0. Some of you will recognize this as the equation for simple harmonic motion. But if you've got to go through the process, that's all cool. You substitute e to the lambda t, you get your characteristic equation, lambda squared plus 4 equals 0. So that's what we call a characteristic equation. Then we've got lambda equals plus or minus 2i. So we've got two complex conjugate roots, and they're actually pure imaginary. So in this case, our general solution, we don't have that e to the real part at the front because the real part is 0, so e to the 0 is 1. We've just got a cos 2t plus b sine 2t. That's our solution to our homogeneous problem. We've now got to go ahead and substitute in our particular guess. So we hypothesize that y is equal to the sum of the solution of the homogeneous problem plus y particular, where y particular equals c, our undetermined coefficient, e to the 3t. What we're going to do is we're going to sub this y into our equation. So we need y equals a cos 2t plus b sine 2t plus c e to the 3t. We need, so remember that our equation is y double dash plus 4y equals e to the 3t. So we're going to need y double dash. Fortunately, they're just cosines and sines and exponentials. So this is actually pretty easy to differentiate twice. So I'm going to do that quite quickly because I think you should know how to differentiate cosine and sine by now. I'm going to do them both at once. I'm going to get cosine back again with a minus sign, and I'm going to get a factor of 2 squared out the front. Sine is similar. And remember, when we differentiate exponentials, we just get exponentials back, so we're going to get a factor of 3 squared. Okay, now we've got all our ingredients. We just plug them in here and see what we get. It's quite a long expression. So minus 4a cos 2t minus 4b sine 2t plus 9c e to the 3t plus 4 from this factor of 4 here, 4a cos 2t plus 4b sine 2t plus 4c e to the 3t. That's equal to e to the 3t. That's what our equation tells us. Now, what's interesting is this bit cancels with this bit. We note that this comes from the homogeneous part. This is y homogeneous double dash plus 4y homogeneous. Now, we know that that must be equal to 0 because it's literally the homogeneous equation, and that is always equal to 0. This always must happen in this process. So it's instructive to substitute the whole thing sometimes, but it's not actually necessary. You only need to deal with a particular part here. However, when you're learning, it's a good idea to substitute in the homogeneous part as well, because this acts as a check of your work. If your homogeneous part did not disappear, you've made a mistake somewhere and you need to go back and check your working. So this is a good little error trap. When we cancel all this out, we find 9c e to the 3t plus 4c e to the 3t equals e to the 3t, which implies 13c equals 1 after we cancel everything out. So implies c equals 1 over 13. Now we've got all of the information that we can glean from this problem, so we can write out the general solution to the inhomogeneous problem. All right, we've still got two unknown coefficients, or two unknown parameters in this problem, a and b. If we had initial or boundary conditions, we could substitute them in now and find the a and b. But I don't have initial or boundary values, so I have to be content with the general solution.